Consistent beer quality, guaranteeing that the bottle you open today tastes exactly, and I mean exactly identical to the one you popped up in a year ago. Well, it's not magic. And it definitely isn't just brewer's intuition. It's actually a multi-dimensional systems-level property spanning microbiological, chemical, and physical dimensions. Welcome to today's Explainer. We're going to dive deep into the rigorous analytical measurements and statistical process controls that actually ensure that quality. If you're a food technologist, a brewer, or a process engineer, this is for you. We're looking at the actual physics and biochemistry required to engineer a flawless beverage, time after time.
Here's our roadmap for today. We're covering data systems and specifications, core beer quality parameters, wort production and fermentation, maturation to bright beer, packaging quality assurance, and finally, automation and correction.
All right, Section 1, Data Systems and Specifications. Let's talk sampling schedules.
Now, consistent quality absolutely requires specifications, tight tolerances, and rigorous sampling schedules. Why? Because you simply cannot control what you do not measure. A truly universal sampling schedule ensures these key measurements are taken across the entire process, long before a consumer ever detects an off flavor. Just look at the frequencies we're talking about here. We aren't just testing the final product at the end of the line. No way! We're testing raw materials at every single delivery to monitor supplier reliability. We're tracking unfermented wort for every batch, analyzing fermenting beer every 12 hours, and testing beer in the package for every code. We even rigorously test the plant equipment itself on a weekly basis to monitor cleaning performance. This sheer volume of data is exactly what allows process engineers to see the invisible mechanics of brewing.
But here's the thing. When you generate that mountain of data, how you analyze it totally dictates your success. Simply highlighting a single defect is definitely useful for making an immediate pass-fail decision, like say realizing a tank is out of spec and blocking that bad batch. But moving to statistical trend analysis, that's a real game changer. By plotting data over time, process engineers can actually predict and prevent future defects by adjusting upstream variables before a process spirals totally out of control.
And this preventative mindset relies heavily on control charts. Tools like three-point moving averages and cumulative sum graphs or CUSUM graphs become absolutely essential for isolating those underlying shifts in your biochemical processes. For instance, a wide distribution curve on a histogram tells us right away that the process is out of control, while a nice narrow one means we're perfectly dialed in. Plus, by plugging all this into computer databases, we can ditch the cumbersome paper records and let the system automatically generate these crucial visualizations for defect highlighting.
So, let's break down how a CUSUM graph actually works. The crucial point is that we subtract our actual result from a target middle specification. Let's say our beer color target is 12.5. If our actual sample comes in at 13, we have a difference of plus 0.5. We cumulatively add these differences sample by sample. If everything is perfectly in control, the line just runs flat right at 0. But if our color starts creeping up, this cumulative math instantly and graphically exaggerates that ongoing trend. It lets us spot a deviation long before it ever reaches a critical failure point.
Moving right along to Section 2, Core Beer Quality Parameters. Let's look at how we actually measure the beer itself.
Applying this whole data framework means tracking the universal quality metrics of beer. Remember, brewing involves highly complex, interacting physical and biochemical processes. Managing parameters like pH and dissolved oxygen, or DO2, is a constant, delicate balancing act between fostering healthy yeast and preventing oxidation downstream. Take dissolved oxygen. On the hot side, absolutely vital for yeast growth. But if you have high dissolved oxygen in the finished, packaged beer, it causes oxidation, making the product taste unpleasantly stale, literally like wet cardboard. Meanwhile, trace flavors like diacetyl, DMS, and esters must be kept in perfect balance to ensure the beer remains strictly true to type.
And you're going to see these two metrics everywhere: original gravity and present gravity. Original gravity, or OG, is the specific gravity of the wort before fermentation, while present gravity, PG, is the gravity at the exact time it's sampled. Tracking that drop from the OG down to the PG fundamentally dictates the strength and flavor profile of your end product. The OG tells us our starting potential, while tracking the PG lets us map out the fermentation degree and efficiency in real time.
Okay, Section 3, Wort Production and Fermentation. Let's dive into the hot side operations.
The foundations of our final product are mathematically established long before the beer is finished.
During wort production, variables like enzyme activity, extraction efficiency, and mash pH mathematically predetermine the attenuation limits and color stability of your beer before yeast is ever even introduced. It's fascinating. If you want to hit your precise original gravity, you absolutely must dial in your malt-to-water ratio and extraction efficiency. If you want exact fermentability, your mash conditions, specifically the time, temperature, and pH acting on those malt enzymes, must be flawlessly executed. Furthermore, controlling your pitching yeast requires incredibly strict analytical oversight. You can't just pitch yeast and hope for the best. You have to monitor the physical condition to dictate viability, that is, the percentage of dead cells. You're relying on the health of the previous fermentation to dictate vitality, and you must ensure absolute integrity in your strain separation to prevent microbiological contamination. Plus, your cropping and purging operations directly dictate the yeast count in suspension. A failure here doesn't just stall a fermentation, it literally ruins the entire batch.
Next up, Section 4, Maturation to Bright Beer. Time to look at the cold side.
As we move into the cold side, the mechanistic focus completely shifts. We're now refining and stabilizing this biochemically transformed liquid. Managing a trace flavor like diacetyl becomes strictly a function of the length and temperature of maturation. Meanwhile, beer clarity, or haze, relies entirely on maturation time and temperature, stabilization, and mechanical filtration performance. And notice how absolutely crucial your transfer-in procedures become here. Any air left in the bright beer tank before transfer-in will instantly spike your dissolved oxygen. Literally every hose, every single connection, and every mechanical step is a potential critical control point.
We also really need to highlight that microbiological contamination is, without a doubt, the most destructive defect. Wild yeasts, molds, and bacteria consider beer a perfect food source. A tiny lapse in bright tank or filter main sterility allows these microbes to multiply at staggering, phenomenal rates, rendering the product completely undrinkable. Let me be clear. Sterility isn't just a nice goal to have. It is a mandatory, non-negotiable control point for quality.
All right, Section 5, Packaging Quality Assurance. Let's talk about physical barriers. You could brew an absolutely perfect beer, but without a final physical barrier protecting it, it was all for nothing. At this packaging stage, QA relies heavily on strict mechanical tolerances. We're talking fill levels to ensure specific contents volume, and can seam quality that relies strictly on the seamer machinery performance. A faulty bottle crown doesn't just let beer leak out. Worse, it lets destructive oxygen leak in. And achieving perfect dissolved nitrogen for a stable, tight foam? That depends entirely on your counterpressure performance and direct dosing accuracy operating within exact specifications.
Finally, we arrive at Section 6, Automation and Correction. This is where process engineers really shine.
Despite all these controls we've talked about, deviations will eventually happen. It's just reality. But if a defect is highlighted, quality professionals must never jump to conclusions. Instead, we follow a rigid 5-step investigatory protocol. Step 1, is it real? Always recheck the analysis to verify. 2, what is the extent? Check other batches for similar defects. 3, when and where did it happen? Review those QSIM graphs and concurrent processes. 4, what are the causes? Hypothesize based on anomalous inputs, like, say, an unexpected delivery of new high-color malt. And finally, Step 5, what can be done? You isolate the current stock and systematically adjust future process variables.
To minimize that manual correction, modern breweries rely on automated control loops, where sensors constantly feed real-time data back to a central controller. Imagine this. A temperature probe continuously measures the fermenting liquid. It sends that real-time data right to the control system, which compares the actual temperature to the specification. If the beer's getting too warm, the system doesn't wait around for a 12-hour lab check. No, it instantly sends a signal to the coolant valve. Coolant enters the jacket, and the fermenting vessel temperature is lowered immediately.
These automated systems rely on fundamental physics to track parameters without needing manual lab sampling. It's brilliant. For example, a transmitting resistance thermometer uses electrical resistance to correlate with temperature. To automatically monitor present gravity or density during wort breakdown, a vibrating U-tube sits right in line. As the density of the liquid changes, the resonance of the tube changes mathematically. For DO2 or CO2, a membrane sensor measures the pressure increase of transferred gas. And for cleaning-in-place systems, we use a conductivity sensor to monitor electrical differentials, ensuring our detergent strength is exactly right.
So quality control isn't merely about catching mistakes. It's about engineering a system where mistakes are mathematically prevented. Knowing how rapidly defects can multiply, I want to leave you with this. How effectively does your facility leverage historical statistical data and inline sensors to prevent, rather than just react to, quality deviations? Think about it. Keep measuring, and I'll catch you in the next explainer.